Yeah. Yeah.
Is Ben the senior?
No, he graduated last year. So.
Oh.
Ben did?
Mm-hmm. So for problem number 43, we've got y equals sine of x raised to the x. All right. So now when we look at this one, you might think to yourself, this is an exponential function. We could use the exponential rule. The exponential rule is kind of an easy way to do this. Well, it's not easy. There isn't an easy way to do this. They're all difficult, but there's 3 different ways you could do this. If I treat it as an exponential, we say u to the x, where sine of x is u. Then we take the derivative of u, which would be cosine of x, and then we plug it into the formula. That's one way to get the answer. But since this section is on logs, what we're going to do is we're going to take the natural log of both sides, like this. Now, one of the properties of logs, if you remember, is that when I have something raised to a power, I could take that power and toss it to the front. So what we're going to do is we're going to do that. So in the next step, I have the natural log of y is equal to x times the natural log of sine of x. Okay? Now at this point, now I'm going to differentiate with respect to x. So I'm going to take the derivative with respect to x. And from there, the natural log of y, remember that when we take the natural log, if I say d dx of the natural log of u, that's just going to be 1 over u times du dx. Right? You guys remember that? So then this becomes 1 over y dy dx, because remember we're doing the derivative implicitly. So whenever we take the derivative of y, we treat it like x, but we tack on dy dx at the end. Right? And so then that's equal to, and now for this part, I've got to take the derivative of all that stuff. So that's really the product rule. So when, just to kind of refresh our memories about how the product rule works, if I wanted to take the derivative of 2 things that were multiplied, like u times v, well, that would be u v prime plus v u prime. In this case, we would say u is equal to x, and u prime would be 1, and then we would say v is equal to sine of x, and then v prime is equal to cosine of x. Whoops, cosine of x, right? So the derivative of all this stuff is just going to be x times the derivative of all this stuff, which is going to be, oh wait, it's not just sine of x, it's the natural log of sine of x, which would be 1 over sine of x times the derivative of cosine of x, based on this formula up here, right? Mr. Adams got a little fancy and got a little fast there. So this is v prime here. It's all this stuff. Because we have the natural, let me rewrite this. We have the natural log of sine of x. And so when I take the derivative of the natural log of sine of x, I get 1 over sine of x times the derivative of sine of x. All right. What is cosine over sine, though?
No, tangent.
It's tangent. So let me just write it down, though, and then we'll switch it later. So this is going to be times cosine of x all over sine of x plus v by itself, which is just the natural log of sine of x, times the derivative of x, which is just 1. So I've got 1 over y dy dx is equal to x cotangent of x plus the natural log of sine of x, right? Well, we want to find y prime or dy dx, so I'm just going to get this by itself by multiplying everything by y over 1. That'll cancel with this term in the front, so I get dy dx is equal to y times x times cotangent of x plus the natural log of sine of x. Now, I could clean this up a little bit if I plug in y. All right, what did I say y was? Well, we said that y is equal to sine of x raised to the x. So dy dx is actually sine of x raised to the x times x cotangent x plus the natural log of sine of x. Okay? So now we can verify that by using n derive. Now what n derive does, well, first let me plug this in. So let me clear out my functions. And let's graph the original function, which is going to be sine of x raised to the x. Right? And if I graph it, it's going to look kind of crazy, I think. Yeah. There's all kinds of goofy stuff that's going to go on. And so all this stuff down here on the bottom will help me to find the derivative, which is the slope of the tangent line. So right about here, I don't know, at about 2, I should be able to find the slope of a tangent line. So if I hit second trace and I come down to dy dx, which is option number 6 in your calculate menu, and I just say like 2 equals x, right? My calculator spits out an answer of dy dx equals negative 0.835. Now what that's saying is if I were to go through and finish and find the tangent, the equation of the tangent line, it would have a slope of this negative 0.835 when x equals 2. Okay? Now, there's a couple ways I could verify that. If n derive, without doing the graph, I could do that in just your computer screen mode by doing n derive. So if I hit math, okay, option number 8 is n derive. Now your textbook will say endur, which is like if you have an older calculator, it doesn't. It just says NDER. On the newer calculators, it has this. And the way that works is I'm going to hit sine of x. So I got to plug in the original function. And then I hit comma. And so this is really a computer program. So the first thing I put in is the function. Then I tell the calculator that I want it to evaluate the derivative of x. Then I tell it what number to plug in. So what did we plug in when we did it on the graph? 2, right? So I'm going to plug in 2. Now, when I hit enter, what this does is it just spits out what the slope of the tangent line would be at x equals 2. So if I hit enter, I should get negative 0.835, which is exactly what I get. Does that make sense? Yes.
It's like really small.
Oh, you can't see it on the thing? I can fix that. Can you see it? Okay.
I don't. Right when after you raise it to the x, then what's that like dot?
It's a comma.
Oh.
It's a comma, which is this button right here on your calculator. Now, what we said is that if I took sine of 2 and raised it to the 2, so I'm going to take this equation here, and wherever there's an x, I'm going to plug in a 2, and I'm going to multiply that by 2 times, now we don't have a cotangent function, but I can say cosine of 2 divided by sine of 2, because that's what cotangent is, right? Plus the natural log of sine of 2. I should get this negative 8.35. Let's see. And so what I've done is I've mathematically, and you could choose any number to plug in for x. But this number, which is just x evaluated, we're taking f prime and evaluating it at some arbitrary number. And then I could take n derive, which will give me the number. And so if the two numbers match up, that means you've got the right derivative, right?
What about after the 4 and 1, like, it's not the same, like, after so many decimal points. Does that matter?
No, because the calculator just rounds it up. This first one is an approximation.
Oh,
This one's a little more precise. Yeah. Yeah, but that's like to the 10,000ths, 100,000ths place.
yeah, I thought,
Right.
I was wondering.
What this does is that you guys don't remember it, but this uses that it does whatever it does 2. It just calculates the slope, but it uses the points for x. It uses 2, and then it uses like 2.0001 for x, and then the corresponding y values, and just calculates the slope. Okay. Good. Any other questions? All right. Good stuff.